engineering. And today I'd like to talk to you about polymer electrolyte membrane fuel cells. So it's a bit of a shift in topic, and I'll give you a little bit of background information so you can follow some of the things that we're doing. So just to give you an idea of where I'm coming from, the University of Toronto is at the southern point of Ontario. And let me just point that out to you. So we're at the bottom of Canada there. So there we are. And you may be familiar with Toronto Blue Jays and Raptors, the NBA. So there we have over 67,000 undergraduate students, almost 16,000 graduate students. And because of the international audience here, I thought it'd be interesting to note that we have over 12,000 international students from over 150 countries. So because fuel cells are a bit of a different topic, I wanted to place them in context. I think that many of the talks that we've seen today, or last day and this morning, are concerning the sources that are providing the energy for the services. And so this is an energy system architecture that was coined by Professor David Scott, an author now living at or working at the University of Victoria. If we think about our energy structure as starting with our sources, then we think about the end user and what do they care about energy. They care about being able to communicate, having heat in their homes, illumination, transportation. Those are services. And so if we look at this architecture, we can start with our services, then talk about what are the technologies that give people those services, like telephones, computers, lamps. How do we get energy to those technologies? Well, there's currencies such as electricity, diesel fuel, jet fuel, gasoline. Hydrogen is one of the currencies that I'm going to be using. There's technologies that enable us to harvest the usable energy from our sources. And so I'm in the area of using currencies, converting energy to power service technologies. That's where fuel cells are really sitting in that architecture. So one of the benefits of using PEM fuel cells is it enables us to use renewable energy. Renewable energy is generally intermittent, such as wind and solar, and we get electricity from these sources. What do we do with it? Well, we can use it immediately, or we can save it for later. If we save it for later, we have technologies such as batteries, supercapacitors, pumped hydro, flywheels, and hydrogen is a way that we can save this energy by electrolyzing it and storing it. And so if we do that, we can essentially store hydrogen and use it with PEM fuel cells for on-demand electricity. And so fuel cells, as you may have seen, that they're in a variety of automotive applications now, transportation applications. Forklifts are really getting a lot of traction, and many of the automotive companies are aiming at this year and next year for this year, next year, up to 2017 for commercial production. So one of the benefits of PEM fuel cells, we talk about higher efficiencies, but I wanted to show you one of the kind of very tangible ways where you can see this efficiency coming in. If we talk about a regular heat engine, we have chemical energy coming in. We're converting that chemical energy to heat. Then we have mechanical energy, which we're then generating electricity with a generator. So these sort of several steps involved, 2 conversion steps, and we're converting from chemical, mechanical, then to electrical energy. And this, one of the key steps here is that we have to convert that to heat. Well, in a fuel cell engine, we're converting chemical energy directly into electrical energy. So there's really one conversion step, and that's one of the reasons why we can get some gains with efficiency. And fuel cells have really received quite a bit of attention in the last several decades, and what may not be evident is how much progress we've really made in the last decade or so. So if we look back in 2002, and this is from the Department of Energy, this estimate of the price per kilowatt of energy. Back in 2002, we're at $275 per kilowatt. And to give you some context, the IC engine is around $30 per kilowatt. So that's where we really need to go. And as you can see here, in the last few years, we've really gone down. I think the latest estimate is we're around $45 per kilowatt. So we're getting close. The dollar amount is close. The challenges are very still significant. So to get to squeeze the last dollar, we really have to start working at the nanoscale, microscale and the nanoscale. So this brings me to what I'm doing at my lab. We're the Thermofluids for Energy and Advanced Materials Laboratory. We're working on ex situ characterization, in situ diagnostics, feeding into our numerical modeling to provide design tools for developing advanced materials for optimized PEM fuel cells. This is a schematic showing you how the PEM fuel cells are arranged. Think of it as a series of very thin sheets that are pressed together in a sandwich. We have a membrane, there's a polymer membrane in the middle of the fuel cell, catalyst layers on either side, porous materials then on either side where we're bringing in, diffusing, and distributing the fuel gases, hydrogen and air, and they're delivered by these flow fields, these channels in our current collectors. And then these are combined together and assembled under a sensitive amount of pressure to prevent leakage, yet we cannot destroy our materials either. Now, in these fuel cells, we have a delicate balance of liquid water, and that's one of the main topics of my research is how to manage the structural properties of the fuel cell, and here's some pictures of these materials, to get us the transport of gases that we need. We have liquid water so that we can provide ionic conductivity to the polymer membrane that needs hydration, yet too much water essentially drowns the fuel cell, clogs all the pores so we can't get any reactions taking place. We have to do some understanding of these materials so we know the relationships for continuum modeling, for example, saturation versus capillary pressure, permeability versus saturation. One of the tools we're using is computed tomography to obtain a three-dimensional image of these materials. So this is on the left is a nano-computed tomography image, which gives us this three-dimensional X-ray of the material at the nanoscale resolution. This image has a resolution of 50 nanometers, is the smallest spatially resolved feature we can obtain. And then we can look at what are the properties as we step through this material, going from bottom to top, or also left to right. So we can look at through-plane slices, in-plane slices. And another important tool I wanted to show you is that, well, because fuel cells are pressed together in that sandwich that I showed you, it's opaque. You can't just see what's going on. You've got metallic plates, carbon plates, you've got carbon and platinum in the catalyst layers, so it's not an easy matter of just seeing what's going on at the microscale. So we've been using synchrotron radiography to visualize what's happening in this fuel cell. And this synchrotron enables us to take an electron beam, and there's a handful of synchrotron facilities around the world. And when you have this electron beam, it provides us a really high energy light source. And at various points, you can essentially leak out some of that light. And using monochromators, you can fine-tune the energy of the light and the wavelength of the light to essentially provide an X-ray. So we're using X-ray light to peer inside of the fuel cell. And if you see here, I've shown you the assembly that we're using where there's these pocketed holes in selected places so that we can provide this beam penetration. So here's the arrow showing where we're putting in directing the electron beam, the X-ray beam. And depending on our orientation of this special cell, we can see the accumulation of liquid water. So what I'm showing you here is it's a cross-section of the fuel cell, and the white bits are where there's liquid water appearing. Okay, so what I'm going to show you now is a video of liquid water appearing in the fuel cell. When there's no water, it's black. And when you see liquid water, it becomes white. Because when water appears in front of that X-ray beam, the water attenuates the signal. And so where there's attenuation, we know that there's liquid water. On the left-hand side is the in-plane image, and the right-hand side is the through-plane. So we can see in both directions of this planar fuel cell. So the impact here is that the material is opaque, it's porous, but because we have this synchrotron tool, we're able to visualize the appearance of liquid water, the transportation of it in the channels, and this dynamic behavior over various conditions, temperature, and current density. So in our group, we're doing a lot of work to characterize the porous materials and simulate them, because once we can simulate them accurately, we now have our design tool. So in the top, what I wanted to show you is this is our micro computed tomography imaging of the material, and the bottom is our numerical representation of it. So this is something that we've been working really hard at to be able to simulate something that's accurate. Simulating this material involves various steps whereby we populate a space. So for example, we're now creating this fibrous carbon material, and we start with a domain and we populate this space with fibers according to the porosity information that we've obtained with our computed tomography. And so we place these fibers according to this statistical probability that they will exist. And then we place this binding material that we know exists in these materials, and we place it that in a way we assume it's a wetting property, a wetting behavior when it's applied. And then we have our solid and our void constituents of the material. And then we need to know, if we want to simulate how liquid water flows in the material, we need to know precisely where the porous spaces, the voids, versus the solids. And it may seem trivial, but when you are doing some simulations, this distinction is really important. And so we perform a distance transform to obtain the pore space information. And this distance transform involves some growing of pores. And we do this so that specifically we can use a technique called pore network modeling to simulate how liquid percolates through this material. Continuum modeling like CFD certainly can be used, but definitely a very small fraction of it can be applied in the same time period because of the computational cost. So we use this technique called pore network modeling, and what essentially happens is that we can distill the important physics from the Navier-Stokes equations, fluid transport, and then simulate how the liquid water and the interfaces will percolate through this material. So this is, in closing, I'm just showing you a simulation of how we're simulating this liquid water transport in a gas-saturated medium using our software, which is called OpenPNM, and we've been developing this in collaboration with McGill University and Automotive Fuel Cell Corporation in Canada. And so from this now, once we have this information, we can calculate diffusion, permeability, and start to design some materials tailored for fuel cells and other applications. Another application we're also working in is in carbon sequestration, and using this tool to understand what are the stability of various sequestration materials. Thank you. So just in closing, this is again my group, and we are working in using ex situ characterization, such as the X-ray imaging that I've shown you, synchrotron radiography to look at operating fuel cells, and we use all this information, validation, characterization, to feed into our numerical modeling tools. And this is my group and my contact information, and I would be delighted to answer any questions that you may have. Thank you.